Hi everyone, Mr. Lee here. In this video, we are going to go over the graphical nature of the period of a pendulum. Okay, and so this video is actually going to go over a lot of the topics that we once uncovered way back in the kinematics unit. And so we're going to do a quick little reminder of that. All right, let's get started. So before we actually begin into the graphs, let's go over the idea behind the nature of a pendulum. Okay, now a pendulum is simply a object. We call that object a bob or a hanging bob, and it swings back and forth, back and forth, back and forth. Okay, so that is a pendulum, and we say that the period of the pendulum, the equation is 2 pi L over the square root, or L over g, the acceleration due to gravity. And we see here from this equation that only the length of the string and the acceleration due to gravity actually affects the period of a pendulum. Now, let's go over the graphical nature of this period of a pendulum. So if we have a pendulum and it swings back and forth, and we were to find a position versus time graph, okay, for the x-axis. Now, what that means is if we say that at this point right here, this is position of, I don't know, let's say this is, negative x. I don't know what that is, right? It could be anything. And over here, we say that this position is positive x. Okay, so we have negative x and we have positive x. And right here, right there in the middle, we're going to say that as x is equal to 0. And the reason why I'm using negative x and positive x is because of the nature of the pendulum. Now, if you remember, according to the conservation of energy theorem, this pendulum, if you release it from a certain height, on the other side, it'll raise to the same height. It'll come back to the same height. Right? No energy is lost, no energy is gained. So the gravitational potential energy here is equal to the gravitational potential energy here. It's the same. Now my drawing is kind of a little slanted, and so it doesn't look like it, but trust me when I say it, it's the same. And so that's where this idea comes from, where the initial or this negative position has to equal to the positive position, and the exact middle area here is what we can call 0. All right, so let's say that you raise up this pendulum. Okay, so you raise up the pendulum to position, let's say negative x. Okay, we raise it up to this part right here, and then you say 3, 2, 1, boom, and you release the pendulum, and the pendulum swings back and forth. Right? Back and forth, back and forth, back and forth, back and forth. And time continues on. And what you would get if you were to collect the data from this, if we were to do a position versus time graph like so, we started off here at negative x. Okay. We would see that it goes up. So we say that this is negative x, and we say that here this can be positive x. Okay, whatever value that is. You can say that is, I don't know, 10 centimeters or 5 meters, whatever you want. Okay, but we just know it goes from a negative to a positive. And then after that, so this is from swinging from this position over here, and it swings out. I'll use a different color so you can see it. So it swings out, right? And that's where we are, right here. We are currently in the positive position. So after there, it'll swing back over. And so it'll look something like this. Whee! Okay, kind of like that. And then it'll be back to its original negative position. All right, and then this will go on indefinitely. Wow, that's just a really fancy way of saying forever, in the theoretical sense, where air resistance is negligible and there's no friction and none of that. And so I will continue on this x-axis here. I'm going to make this a little bit longer. So it'll just go back and forth, back and forth, back and forth. And you notice here we have what we call a sine-like curve, or a sinusoidal curve. Okay, so a sinusoidal curve. Now that's just a fancy way of saying that we created waves on our graphs, or we created a graph where the line, the curved line, represents a sine graph. This term is very important because oftentimes in the problems you'll see this term being referenced as sinusoidal. Okay, so here we have a position versus time graph where position is in, of course, meters and time is, of course, in seconds. Now let's break this down. I want to do the reminders first, back from the kinematics unit. Now this is something that you should have down in your brain, and in case you don't have it down in your brain, you should have it down in your notes so that you can have it down in your brain. For a position versus time graph, the slope, everyone, the slope represents, good job, your velocity. Okay, the slope represents your velocity. Now, we're going to do a reminder within a reminder. So I'm going to go back up here. Now, we said that up here we started off with gravitational potential energy. Okay, and that gravitational potential energy, as it's swinging, it turns into kinetic energy. Now, we also say that when it is raised at its highest point, the kinetic energy is 0 joules. There's no kinetic energy there. It's not moving. That's very important. Okay, at positions x and negative x, there is no velocity. And so what I'm going to do is I'm actually going to put tiny little stars using my galaxy pen at those points. So this is x, this is positive x, negative x, positive x, negative x, positive x, and so on and so forth. Now this is important because I'm going to put a little notation here. Wherever we have these stars, the velocity is 0 meters per second, and that's because you have gravitational potential max, and kinetic energy is therefore 0 joules. Okay, there's no motion whatsoever. And so if we go back to this idea that the slope represents velocity, we can state that at these marks, these starry marks right there, your slope is 0. Yeah, very important. And so what does a slope of 0 look like? Well, a slope of 0 is a flat horizontal line. Okay, and so at that point right there, I'm going to use red so that it kind of stands out. At that point right there, if we were to create a slope of that point right there, we would get a flat line, like so. It's a slope of 0. And then we could repeat this for every single part. So this is a slope of 0. Oops, that should be a little bit more flat. This, of course, is a slope of 0. Okay, and because at those points, your velocity is 0. It's always going to come back to this idea of velocity. Now, if we were to go back to this drawing here, we know that at the highest point, at the peak, the kinetic energy is 0. And therefore, at its lowest point, right here, at position 0, okay, that is where your kinetic energy is max, and your gravitational potential energy is going to be 0. Okay, that's going to be where your gravitational potential energy is 0. And so what does that mean for us? That means that it is moving the fastest at the lowest part of the swing. Very important. We can state that here when x is equal to 0 meters, or position meters, 0, it is moving the fastest. Okay, it's moving the fastest, and gravitational potential energy, we are going to claim it to be 0, assuming that that is the height of 0 that we started off with. And so KE will be the max. Okay, now how is this represented within the graph? What that will tell us is that no matter where we look on this graph, the slope, and I'll do this highlighted, the slope of these highlighted parts, okay, that will be the greatest slope. And so I'm going to try this also. I'm going to try blue here. Let's make it a little bit thicker. So here, if I were to find the slope of that blue point right there, okay, that slope, that is the greatest. And this right here, this is also the greatest, but negative. This right here, greatest, but positive. This right here, greatest, but negative. And so you're hearing me say it's positive or negative. So how do we know if it's positive or negative? Well, if we go from lowest time to greatest time, the line right here is going upwards. Okay, the line is going upwards. Therefore, right here we have the positive velocity right there. Okay, it's the greatest positive velocity. And here, because it's moving, this line is moving downwards, this right here, we have a negative velocity, and it'll be the greatest negative velocity. And right here, because it's moving upwards, okay, we have the greatest positive velocity, right? And then let's follow this trend right here, because the slope is 0, not moving, okay, it comes to a stop, and then it speeds up again. Whee! Right? And at this point, it's moving as fastest, and it's negative. Okay, so the trend continues over and over. And the velocity is the same for here, for here, for here, for here, all this, or excuse me, the speed is the same for all those, but the direction just changes from positive to negative. Okay, very important. All right. So we broke it down using our previous units as a reminder of really how to interpret this graph. So let's do a quick recap. All right, at its highest points, its maxima and its minima. Okay, maxima means highest, minima means lowest. We have the greatest gravitational potential energy, and the velocity is 0, and we know that because the slope is 0. Okay, right in the middle where it crosses the x-axis, right there, okay, because it's the halfway part, this is where we have V max, okay, maximum velocity, or the speed is the max, all right, and it's going to go back and forth. So what we're looking at is a pendulum that is swinging back and forth. All right, so up until this point, this is just a reminder of the previous units of kinematics and energy. Now let's add the new part. The new part is this idea here called period, capital T, where things start to repeat itself. So if I were to ask you to analyze this graph and tell me the period of the graph, this is what you would do. The easiest thing to do is take a look at where the graph starts, which is usually at 0 seconds, and see where the shape starts to repeat itself. And that's what we call a cycle. So if right here, we can say at this point, this is t equals 0 seconds, okay, right there. And then we can see where it starts to repeat itself if we follow the line, right? So it goes up, wee, right, and then it falls, whoa, right? And so at this part right here, this part right there, that is the completion of one cycle. And so however long it takes, the time it takes, so I'm going to say t equals t, t final, right? I don't know what that is, but however long that takes is one period. Okay, and we could do the same for each of the major points. So if we were to find the period from, let's say, this maximum velocity, okay, maximum positive velocity, in order to find the period, we will see how long it takes to go from one maximum positive velocity to the next. And so we would, I'll highlight this. Actually, yeah, I'll do this in highlighted. Let's see if I can do a different color. Oh, I can. All right, I'll do this in green. All right, so one period would go from there. It's going to go down. Now we don't end there because that's a half a period, because that's maximum negative velocity. I'm going to go back up, and right there, however long that highlighted portion takes is considered to be one period. And one period, it never changes, right? So if you we'll try this with numbers here. So I'm just going to do a quick little sketch, position versus time. Let's do something like this. Whee! All right, so a very rough sketch. Probably, I don't know, it looks pretty ugly to me. I'm not like Bob Ross. I do make mistakes, and they're not little happy mistakes. Okay, so we'll say that this is t equals 0 seconds, and I'll say that this is t equals 1 seconds right here. This is t equals 2 seconds. Right here is 3 seconds. Right here is 4 seconds, 5, 6, 7, 8, 9, 10. And the way that I broke down this graph is I just took, I added the time interval for the major points. So I'm going to show you that with my dotted line. So major point there, that's a maximum velocity. Here we have a minimum velocity. Once again, a maximum velocity. Here we have a minimum velocity. Here we have a maximum velocity. Okay, so you're catching my drift here, right? Okay, so if I were to ask you, determine the period of this pendulum, of this graph, right? So I'll do this with a highlighter. The best way to do this is you can start from any point, actually. So the easiest way to start is actually at 0 seconds, because you don't have to do any fancy math. But I see here we have a maximum position of positive x, and then I'm going to go until I reach another maximum position of positive x. Right there. All right, and so I take a look, and this highlighted curve, it took a total of 4 seconds. So I would say that the period would be 4 seconds. Okay. Now we can also do this, and I'll do this in green, a green highlighter. Here we go. Actually, let's do a red highlighter. Okay. I can also do this for if we start here, let's say at 2 seconds. Okay. So if I start here at 2 seconds, and I go up, right there. All right, so I'm going to mark it. So we have right there to right there. Okay, so the period should be 4 seconds, and we can see this because your time initial, okay, remember delta t is time final minus time initial. We know that time final is, so this is 4 seconds, 5 seconds, 6 seconds. So we have 6 seconds minus your time initial, which was 2 seconds. So we get a total of 4 seconds for the period, and that is the same that we said above. So the period for a pendulum, it never changes. Okay, so that's how you can find the period according to the pendulum. One last thing that I want to show you right before the recap is what these graphs look like in the real world. Okay, in the real world. So far, these graphs are very theoretical physics. Like, what would happen if there's no air resistance, if there's no friction, if there's nothing that's taking away the energy of a pendulum? And so that's the big idea here. All of these graphs, we had perfect amount of energy, no energy left the system, there was no heat generated, none of that. So what we get is this looking graph. So it looks like a normal pendulum. But then the amplitude decreases. Okay, and the amplitude simply means the maxima and the minimum. So what this shows us is if we have a pendulum, and it swings back and forth. With every back and forth motion, it goes up higher, or it goes up lower and lower and lower until it finally just comes to a stop. Okay, it doesn't rise up as much, and this is what we call damping. Okay, and that's when the pendulum it gets damp, right? The energy gets slightly taken away. But the important idea here is that the period of the pendulum doesn't change. And that's, I don't know about you, but I think that's pretty cool. And that is because the period of a pendulum is determined by the length of the string, and that doesn't change, and the acceleration due to gravity, and that doesn't change. It just doesn't go up as high. Okay. All right. So major ideas. Let's do the quick recap. We went over damping. So this is what the graph will look like in the real world. We also went over why the period of that pendulum, it doesn't change, and it's because of the two variables that actually affect the period of a pendulum. We went over how to find the period of a pendulum based on a graph if they give you the time. Okay, and then we did a very extensive review of how to read a position versus time graph, and this is very important. And we looked at this position versus time graph where we have maximum velocity, zero velocity, and we actually tied that back to the energy unit. And we also related it back to what it means to us, right? When is the pendulum swinging the fastest? When is the pendulum at its highest point? When is it at its lowest point? And we did all of that through the lens of energy. Okay. All right. So that is the graph for a period of a pendulum. In the next video, I'm going to go over the period of a spring. Bye-bye.